Hi, this is Josh with a quick review of one of these classic Euclidean constructions that was posted on Facebook. I'd like to share with you my solution, and hopefully you'll enjoy it. And I'll just talk through my method for solving this. Here you can see in this construction, there's a floating point n. You draw 1 unit and then turn 90 degrees, go out a distance that seems to be greater than 1, then stop at this point, span a circle or semicircle, and then connect your semicircle from end to end, right? Then draw from n to k such that you're choosing k so that n to k is the same distance k to L. Okay, if this is a straight hypotenuse from this point, then you sort of have to choose the right angle. So you have to aim perfectly through n so that the distance nk is equal to kl. So the question is simple. It's what's the area of this red square? So before I go through the method of finding the area of this square that's highlighted in the drawing, I'm going to go over a couple of the basic ideas of simple compass and straight edge constructions. So here's if you have a straight edge, you can draw a line along the straight edge, and it doesn't have to be marked like a modern day ruler. Just be a straight edge, and you just draw the line here. But here I'll mark at the start of this segment, and then I'm choosing this X mark as my unit, right? I will define as 1 unit of length. So then the question posed by a teacher in basic geometry is, how do you double the length of a line segment? So the student says, well, what do you mean? You mark off, the same distance. Teacher says, well, the rule is you're only allowed to use an unmarked straight edge and a compass. So student says, oh, I know. You open the compass and you place the pin here, and then you draw with like the little pencil here. And then you fix it so that it's that same radius. Then you move the pin over to this spot here. And then if we were to draw a circle, the distance from here to here is the same length as from here to here, because we move the pin from here to here. So we could continue this, move the pin here, and then draw off the same distance again. And we can mark off equal distances going down the road as long as we so desire. The teacher says, well, great, you have a compass and straight edge, you figured it out. But how do you double the area for me if we draw a unit square, right? And we'll show you how to construct using circles, maybe perpendicular lines, mark off the same distance, and now we have this black unit square that's 1 by 1. So students get to work, they go to their desk, and then they're like, okay, well, let's draw double the distance along this way and double the distance along this way. That must be double the area. But it turns out if you make this side 2 and this side 2, 2 times 2 is 4. So you've more than doubled the area. You've increased the area 4 times. So now what? So you're on the right idea that you should expand the sides, right? Like if we were had a backyard porch and we wanted to make it twice as large, the porch in area. But we have to stop somewhere in between 1 and 2 times the original side length. So if you made it to 7th grade, 8th grade, and you started to learn the Pythagorean theorem, you were very proud to know that, oh yeah, a squared plus b squared equals c squared. So 1 squared plus 1 squared equals 1 plus 1 is 2. So this is the length square root of 2. If we were to square along this diagonal, the area of that larger square is precisely 2. So you learn this, and I think we did have some proofs of this, but if you have a calculator, it's 1.414. It's an irrational number, but that would be the distance. Furthermore, if you learn these spiral growth patterns, if you had a fun middle school or high school teacher, this is 1, 1. This is the square root of 2. But if we draw a 90-degree angle here, then since that's the square root of 2, 2 plus 1 is 3. You get a new hypotenuse, the square root of 3. Square that, 3 plus 1 is 4. This hypotenuse is the square root of 4. Draw another 90-degree with a single unit. And as we span around, we get this seashell growth. Each of these extensions are 1 unit, but they're at 90-degree angles, and we get the sequence of square roots. These blue lines are the square root of 2, the square root of 3, 4, 5, 6, 7, 8, 9. Actually, that last one's the square root of 10. But we could then take those measurements, span them with if we draw it, like here's from 1 to 10, then we can just measure off with our collapsible compass, but measure off any of these square root measurements that we need for our various constructions. So let's go back to the problem at hand. So here's the construction. And first thing I'm going to do is I'm going to just erase those words and just set it up as follows. So it's 1 unit from that center point N down, and then I'll call this distance to the beginning of the diameter on the left side here, X. So X to here to here is X, and also here to the end of the diameter is also X units. Since we have 1 here and we have X, I'll call this hypotenuse distance Y. Then we have this third line segment that's unknown. We'll call that Z. This is Z squared that we're trying to figure out, which is the area of the red shaded region. So what this construction is sharing also is Thales' theorem, or the semicircle theorem, which states that if you have a semicircle, diameter of a circle drawn, it always forms a right triangle with any point on the circumference. So this point here that can slide along the arc of this half circle is connected here. That must be 90 degrees. Furthermore, we were given that this was an altitude, this 1 unit that goes to the diameter here. That would be the center. And so we have a 90-degree angle down here for this upright triangle with hypotenuse Y, and for this inverted triangle with hypotenuse 2x, right? It's upside down, right? So the hypotenuse is opposite the 90-degree angle. It's the large triangle. So here with the Pythagorean theorem, I'm going to write down the measurements. 1 squared plus x squared is y squared. And a little trickier for the inverted triangle, z squared is the short side, plus y plus z squared equals 2x squared. After we analyze the right triangles that are useful for this proof, I'm just going to put them in a little box that we have these two formulas, and we know that these relationships are true based on these labeled measurements. After trying the Pythagorean theorem, let's try classical proportions of similar triangles. Okay, since they share this blue angle here, the upright triangle and the inverted triangle, and they also both have 90 degrees. By the angle-angle theorem, they're similar and the sides are in proportion. In particular, if we go to this sort of starting the journey of the diameter over here, and this spanning arch above this journey that's 2x units, we have the sine of this angle will be the opposite over the hypotenuse. So for the small triangle, we have 1 upon y. And for the large inverted triangle, the opposite side, yes, is z from this angle, but the hypotenuse is the diameter, is 2x. Cross multiplying, we get the relationship that y times z equals 1 times 2x, yz equals 2x. Going back to the start of this diameter journey underneath the semicircle, we have the cosine. Well, the cosine is the adjacent side x over the hypotenuse y for the small triangle. And for the large inverted triangle, a little trickier, y plus z is the base, and the hypotenuse is 2x. That's the adjacent side. What just happened? I just lost my pictures. There they are. Okay, I'm back. All right, cross multiplying here, we get that y times y is y squared plus yz equals 2x squared. After I do the cross products, I could write those down, but I saw that since y is equals 2x and I'm looking up above, then I know that if I expand out this with FOIL, there'll be some yz terms. That might be useful, but I have 3 variables and I want to see if I can do any substitution steps. So instead of writing y squared plus yz equals 2x squared, I moved yz to the right side, subtract yz, but I know yz is 2x. So I write down that y squared is 2x squared minus 2x. So here are 2 relationships that I'm going to use for proportions. So now I have these 4 formulas, but I want to solve for x. I want to know the radius of this amazing semicircle. So looking at the first Pythagorean equation, 1 squared plus x squared is y squared. And from our analysis with the cross product with proportions using the cosine, we have that y squared is 2x squared minus 2x. So I'm just setting them equal. 1 plus x squared equals 2x squared minus 2x. Now I have a quadratic equation, which I can solve by setting equal to 0. 0 equals x squared minus 2x minus 1. Here the coefficients a equals 1, b equals -2, and c equals -1. So using the quadratic formula, x equals -b plus or minus b squared minus 4ac over 2a. We get 2 plus or minus 4 plus 4 over 2, which is 2 plus root 8 over 2. Now I didn't write down the negative solution because 2 minus root 2 would give us a negative distance. And since we're in 2-dimensional geometry, that's extraneous. We don't need to use that. So root 8 is the same as root 4 root 2. Square root of 4 is perfectly 2. So we have 2 plus 2 root 2 over 2. Divide by 2, and we get 1 plus the square root of 2. And that is x. So the precise radius, think about this. If we move out 1 unit, here it's the altitude. Go 1 unit as if we're going to do a circle of radius 1. But then we go extend beyond our work circle and we go an extra square root of 2. Well, what is the square root of 2? Well, let's see. We already know that that's the diagonal of a unit square. So very interesting that it has to be precisely 1 unit, like a unit circle, plus the square root of 2. And that's x. Well, let's see if we can find y, because we already have the Pythagorean theorem, 1 squared plus x squared is y squared. So we can write 1 plus root 2 squared is y squared, and we can probably solve for y. All right, so be careful using FOIL. We get 1 plus root 2 plus root 2 plus 2 for our 4 terms. And then grouping like terms, 3 plus 2 root 2s. Well, let's pause for a second, because what is 3 plus 2 root 2? It's x squared. So I write down x squared is 3 plus 2 root 2, meaning if we made a square, here's x. So if we drew it underneath this, like if this is our journey from A to B, from here to the midpoint of our journey, if we do like a square underneath that road here, that would be 3 plus 2 root 2. But then what's the square of y? Well, amazingly, since we have this spiral growth, we just add 1 for the short side, it'll be 4 plus 2 root 2, meaning that whatever the area of this red square is, this hypotenuse under consideration is precisely 1 unit of area more. Next, we can use the information from the squares to solve for z, because with the other Pythagorean theorem of the large triangle, we have z squared plus y plus z squared equals 2x squared. Expanding using FOIL again, we have z squared plus yz plus yz plus z squared is 4x squared. Grouping like terms. I used my proportions to substitute. So y squared is the same as 2x squared minus 2x. As I said, yz equals 2x. And then these cancel. Cleaning up, we get 2z squared plus 2x squared plus 2x equals 4x squared. Subtract 2x squared from both sides, subtract 2x. We get 2z squared equals 2x squared minus 2x. Divide by 2, and z squared is precisely x squared minus x. Amazing, because in our journey from using the lower triangle and figuring out the radius, we do know what x is. And because we had to square it for it to find y, we also know what x squared is. So last step, z squared equals 3 plus 2 root 2 minus 1 plus root 2. 3 minus 1 is 2. 2 root 2's minus 1 is square root of 2. And z squared, the area of this red shaded region, is precisely 2 plus the square root of 2 square units. There's a little bit more here to think about, because we have the relationships between the squares written out here, and it seems very interesting. Whatever that area is for x, y is just one more unit of area, precisely one more unit. Amazing. But then if you look from y squared to z squared, well, half of 4 is 2. Half of 2 root 2 is the square root of 2. So if I were to draw them as squares, here, as I said, remember, we started A, and we're going to have a journey. Here's the midpoint of our journey. If we're going to journey from A to B, we planned it out. This is the semicircle spanning above our amazing journey. You can see that the area of this squared, 2 plus root 2, but the area of this hypotenuse, 4 plus 2 root 2, and the area of the red square was 3 plus 2 root 2. But this goes back to these problems of antiquity. Here was double the area. We have double the square. The doubling the square student exercise. Here, the present square that's being doubled is this red shaded square. And the green square, which is the hypotenuse of this upright right triangle, is precisely double the contained area of the red shaded square. All right, so amazing exploration. And as you navigate these constructions, I hope that this video was interesting to you. Again, in exploring the relationships between Pythagoras and proportions, even with a simple construction such as this. But it also touches on Thales' theorem, spiral growth, many other relationships that are simply inherent because you're using a compass and straight edge. So I hope you're enjoying your studying math, and thanks for watching my video. If you can, please like and subscribe to JSMWNYC. I'm a math teacher, tutor, and educator here in New York City. Have a good night, and thanks for spending time with me. Take care. All right. Thanks. Bye-bye. See you around.